Okay, so thanks a lot for the introduction. Really happy to be here. So I guess jet lag is kind of hitting me. So if you find like I'm not like I don't know what I'm talking about, let me know, right? And also feel free to interrupt me with questions. So I'll just let me see if this works. Okay, so I'll just go over first the outline here. Roughly there are 3 parts, but I don't think really I'll have enough time to go over every single point on this slide deck. So I'll make it available and feel free to kind of check out later. I'll give or start with a little bit of kind of a historical perspective on why we actually want this kind of thing, right? And then talk a little bit about the impact on database systems or things we have done recently in the community. But I'll try to be brief over here, but there's actually quite a bit of details that I don't actually want to get into, but they're on the slide. And then I'll perhaps the most interesting part will be the last one, right? Because you have probably heard that the only vendor now just recently pulled off out of the market. Then why should I still care? All right, so let's get started with the first part. I'll start with this traditional hierarchy where everybody is really familiar with, right? So if you talk about the memory, then it's fast but volatile, and storage would be slower than memory, but it's persistent. And then people use caching stores. So we just talked about earlier SSDs, and then we have a buffer pool and cache the hot data there, and the flush changes down to SSD and so on. It's really cost effective. But there are several challenges here, which I'm going to list over here, layer by layer, right? So I think you're going to hear similar arguments or similar facts from owners' talk as well. So I'll be brave. That's also what I really like about this structure of the talks. So if you look at SRAM, right, CPU caches, there's chip area limits, right? So if you look at, for example, AMD chips now, a huge amount of area is actually dedicated to the caches. There's also concerns about energy consumption. Similarly here, in DRAM or memory layer, there's scalability issues, right? We cannot really get down, to kind of scale down the size of the chips and then get higher capacity, right? And also energy consumption issues, right? So if you look at earlier surveys, I think roughly like 30% of total data center power actually goes to DRAM. Storage, we have this, a long problem with higher, average and tail latency. So naturally, we would want something that's, faster, right? It's something that's better with, scalability, high capacity, and also hopefully save some energy. So now this is where the kind of a new memory technology or emerging memory techniques, come to play, right? So the promise here is really high density or scalability. So scalability here means a little bit kind of a different things when we talk about, say, scalability in terms of transaction rates or so on. We want bigger and stuff. But this one, we're talking about smaller and smaller, so that we can get higher density and then get higher capacity. There's several different materials that's been around, and people have been thinking about how to make it work. I'm not a material science person, so I'm not going to really talk about the details. But you probably have heard about these kind of things. First one, like phase change memory or PCM, which is also the currently only commercially available product that's around like 3D XPoint or Optane based upon. Although Intel never said it's really PCM, but people kind of inferred it is. There's also other candidates. The two middle ones are STT-RAM and also this carbon nanotube RAM, which is fairly new recently. And there are 2 companies that I know of that's working on this. They are fairly early in the stage of kind of trying to make this work, or kind of trying to really deliver the promise of high good scalability, high density, and a performance energy profile. Now, of course, there are kind of not so successful attempts already, right? So you probably know that HPE tried on this memory stir idea a few years back with the the machine concept, right? So later they had this proof of concept, which is just really a bunch of DRAM plugged onto the board, and this FE-RAM or electric RAM has been around for a while, but the capacity is kind of small, right? So we're our main hope, was initially a PCM, right? And then, Intel made it work, but then put off. And then the two futuristic kind of things are these two guys, STT and carbon nanotube or NRAM. I'll talk a little bit more about that, in a few slides. But these are the, common candidates that we talk about. Yes.
FSP is still on the market, right?
Which one?
FSP, they're still around?
Yeah, they are.
Okay.
Yeah, so well, both are still around. Right. The second is I think this one is still pretty new, Nantero. All right. So the first one, like I said, that's the only commercially available candidate and was in mass production. And the middle two ones are still kind of in progress, and the final two are, I didn't really see much progress so far. So, there's really a lot of these kind of candidates, right? So you might kind of, when you go through the different materials, then you see, what did we actually want in the beginning, right? So the first one, high density, I've been talking about this quite a bit. And then we want also, good performance. So we want actually to kind of be better than at least the flash, right? And even maybe DRAM comparable to DRAM or even, SRAM, so that we can get better performance and density and also energy behavior in the CPU cache, right? And energy profile, that's what we want, and be embedded addressable so that you can actually use it for, let's say, DRAM or to replace DRAM or SRAM. Ideally, we want cheaper things, right? So, but if you look at all these, right, being persistent is not really in the list. So that's one thing that I think a lot of people kind of didn't really pay too much attention to. But I just want to be to list it here, right? But if you look at all the properties of the previous devices I talked about, they just happen to be non-volatile anyway, right? So all those technologies, they're actually non-volatile, meaning if you pull the power cord, they will still be there, just like flash. Although they work differently than flash, but the effect is that they're persistent. So then basically we have this persistent memory thing, right? If you talk about just the previous properties we talked about, it's just a better memory in general, right? But then once you put this, or you notice this fact that every material we talked about, they happen to be persistent or non-volatile, then we have this particular concept of persistent memory. So then typically these are the properties that we talk about, right, when we talk about persistent memory. Now, because they're persistent, right, you can use it actually to build both memory and storage, right, because they're both byte addressable and persistent. But the performance actually really varies depending on the technology. And often, if you go to a conference and talk to people, we will say, persistent memory is something in between DRAM and flash, right? But actually, if you look at the technology closely enough, there are different technologies for different tiers, right? So STT-RAM can be actually alternative to SRAM. And you can even make trade-offs between persistence, retention, or speed and energy profile to get the desirable property that you want, right? So for example, you can actually trade retention, for how long your data can be stored by that material for actually speed, so that you can get better performance and better energy profile in the CPU cache. Yes.
How about errors? Are they part of the trade-off?
They're also part of the trade-off. Yes. Yeah. But I just didn't list it here.
Correct for the retention, or is it different?
It's different. I think when you program it, there's ways things will go wrong, and then and typically the way you program is by applying, for example, heat. So right. Okay, so this actually can be faster or slower than DRAM. So that's another kind of thing that I want to clarify, right? Now, when we talk about persistent memory, right, because the Optane PMM, since 2019, when we talk about it, pretty much this means Optane PMM, right? And this is a particular product. But it's winding down, right? So I'll talk more about this later. But if you see like future slides, I have this icon over here, that means it's Optane specific. Okay, so I'll get to a little bit more detail about this particular device. It's probably not so relevant anymore in the next few years, but just for the sake of that, it's still here, right? So let's really see whether this device actually delivered the promises, right? So the first big thing is that if you look at the price per gigabyte, it's actually much better than DRAM or much lower than DRAM. If you were to get this 128 gigabyte DRAM, you're spending like 2,000 Canadian dollars. And for the same capacity on Optane PMEM, you're spending like roughly 1/3. Like upper right corner over there, that's the old price or old quote we got about like 2 years ago for the first generation of the server with this device. So basically what you do is to, just to put these devices on the memory slots. And here, I'm not sure if everybody can see this, but if you see this little white block over here, that's actually Optane PMEM DIMM. And next to it would be a normal DRAM DIMM. So they both live on the memory bus, right? So that's why it's pretty much why we call it persistent memory, right? So I'm finally getting to performance profiles. And this is why we call it, it's kind of in between DRAM and flash memory, right? So if you look at the latency numbers and also bandwidth numbers, this is right kind of in between. Obviously, this is slower than DRAM, right? But typically, this would be faster than flash memory. There's, so this one is the oldest or the first generation models. And if you look at the newer models, there will be like 1/3 of performance improvements. I think Lawrence over there had a really nice evaluation of different generations, and you can refer to his paper. I don't remember whether I said it here, but I can give you pointers. Okay, so there's also other candidates, right, other than Optane. So like I mentioned already, carbon nanotube and SSD memory store, these are kind of the real true NVM or true persistent memory devices. But they have been there kind of telling you like real soon we'll have this since 2010. So we don't know actually when they will come. But if you think about persistence, if you really want persistence on the memory bus, you can actually try to quote unquote fake it with DRAM and flash memory actually. And this is what we call NVDIMMs. And this one existed for actually a long time, at least I think more than 10 years or 20 years even. So the idea is super simple, right? You just get some DRAM chips and you get some flash chips, you put them on the same kind of DIMM. And then you also get some supercapacitor so that you have the enough energy to flush things from memory to the flash when power goes out. And then you can load the data back when the power comes back from flash to the DRAM. So this is actually standardized by SNIA, which is the organization that devises these kind of persistent memory and NVDIMM standards. There are different candidates. For example, you can have this NVDIMM-N, which I believe is you use exactly the same size of DRAM and flash memory, so that when your server is running, it's exactly the same as normal DRAM, but it's with some persistence guarantee. And with this NVDIMM-F is something like you use the DRAM as a transparent cache that's controlled by the DIMM itself. But you can present to the server or to the host that you have really this huge memory represented by the capacity of the flash chips. Or you could also, use larger batteries in modern data centers to replace that instead of using the supercapacitor, right? There's charge and discharge costs of the supercap. So if your data center actually has UPS, which is the fact, then apparently you actually have this sort of persistence guarantee already. Okay, so these are also persistent and available today. You can buy them actually, but it doesn't really it doesn't really scale because of DRAM stopped scaling. And also you would have the same speed of as DRAM if you're using this NVDIMM device. But again, the downside here is they're expensive. You're not going to get it in like 1/3 of the price of DRAM chips, like I mentioned earlier with compared to the PMEM device, opt-in PMEM device.
Do you have a sense how such things would fare in terms of energy consumption?
Energy would definitely be more because you you have to do all these extra things. I don't really have.
Itself costs a lot of energy compared to PCM or something.
Compared to PCM, I think it would be much higher, but I don't have the exact numbers here. I think some papers actually try to measure it, but I don't have the numbers, to be honest. Yeah. Any other questions? Hope I haven't bored you too. All right. Okay, so if you look at this, this is actually a major kind of a vehicle to do research before we had Optane PMEM, and also I suspect it might be still the main thing that we're going to use in the future. All right, so now if we compare, right, so what we wanted initially versus what we actually focused on. So the computer architects, they proposed this kind of new memory technologies, right? They're talking about scalable DRAM alternative. They're talking about durable, energy efficient main memory, but we're talking about on the software side, better I/O, better storage performance, and so basically this has led to a lot of persistence and byte addressability kind of put together, so that we can redesign things in single level stores, which is kind of an old idea, but revived under this persistent memory setup. And also things like instant recovery, because if you put everything, all your data structures, all your data on persistent memory, then potentially or conceptually, you can actually get instant recovery. When you turn on the machine, everything will still be there. And also low latency, high bandwidth, right? So these are all the good things we always wanted to have. Right, so there's numerous papers, and more recently, they're all based on Optane, which is kind of both fortunate and unfortunate, which I'll talk about later. All right, so I'll again drill down a little bit detail. If you look at the current Optane devices, there's two modes actually reflected both use cases I listed in the previous slide. On the left, would be this memory mode, which just really presents the system bigger, volatile, but slower memory, right? So you're using the DRAM as a kind of a transparent cache controlled by the CPU. On the right is what software people and also database people really care so much about, that this is the app direct mode, which actually gives you persistence, and you can use DRAM and persistent memory as you kind of like, right? Now the really bad thing, or I think that's unfortunate, is this controller. You have to change the controller, memory controller, to actually make this work, right? So to use this device. So, and also this is kind of an Intel only thing. So it's not, it doesn't work really, for example, if you have an AMD CPU. And I think that's maybe part of the, issue why this didn't really fly. Okay, and how do we actually program it, right? If you think about the whole kind of a hierarchy, right? You have the CPU cache, which is volatile, and then you have the memory layer, which is now persistent. Then apparently things in the CPU cache might actually get lost if you lose the power, and then you have a different copy in the CPU cache and in the PMEM. So there's this technology which is called eADR, or asynchronous DRAM refresh. Basically means if I write something through the memory controller and down to the device, there's a place where I can guarantee persistence, right? If you're and this is actually the right pending queue and others and other buffers in the controller, so that if your data is actually there, for example, after I issue CL flush, it will be guaranteed persistent before it actually gets to the actual device. So if you look at this example over here, I have one thread, and I'm writing to some kind of the data in the cache, and I'm manipulating this pointer pointing to this copy in PMEM. And then you change it to maybe add another pointer over here and so on. And then you hit a crash, what might happen is that you have this thing kind of in PMEM, right? So you lose this pointer over here actually. Then this whole linked list becomes unreachable. So you would need actually to have cache line write back instructions inserted to your code to actually make this work. And also notice here that being visible over here in the cache doesn't mean it's already durable, right? So this is without this ADR or eADR concept, which is a new feature introduced in later Intel machines. Again, I guess it's not so relevant, but just for the sake that it's still here. Basically, the effect is that I'm also including the CPU cache in the ADR domain, which means you don't need to actually insert the cache line flush instructions anymore. But you still need to insert fences to make sure the order you persist data is correct. All right, so there's a lot of tools that people developed along the way to actually make this kind of a more smooth or easier. But the basic idea is really you have this DIMMs and you do an mmap to your address space so that you can directly program it using load and store instructions. So I don't think I'll go to a lot of details over here, but there's a lot of different tools. One thing I want to mention is that what's usually guaranteed or also assumed is this 8-byte atomic array, which is the fundamental assumption that we make pretty much in all the papers and all the actual work. Otherwise, it won't really work here. All right, so now I'll talk about quickly, I hope, yes, the impact on database systems, which is actually in the title, but looks like to be the most brief part of the talk. There's impact on both DBMS architecture and also individual components. So now if we consider the design space of database systems in this context of persistent memory, we have to think about the reality, right? We have machines that will actually definitely come with DRAM and SSDs or hard drives, right? Where we're not going to actually have machines with only persistent memory, at least for now. So this basically means how do we actually use the available DRAM, PMEM, and SSDs? Now, points to consider. There's different things, a few different things, right? So capacity, how do you place different things according to the kind of capacity you need? And the performance, because these are different devices, right? So if you have this PMEM layer in between, then you might consider, say, like, do I want lower or more stable latency or high throughput than flash, or maybe a higher or less stable latency and lower throughput than DRAM, right? And there might be exceptions here when you compare to flash, which I will talk about later. And that's perhaps also another reason that this didn't really fly so far. Okay, and also cost is a big factor. I think a lot of work actually kind of omitted or didn't or haven't really cared to consider too much, but it's really important. All right, so I'll talk more about the exceptions later and fine prints. So in terms of architecture, really there are two major ways to adopt this. One is that you can try to fit persistent memory as a new layer into the current buffer pool architecture, right? So it just now becomes 3-tier or even more tiers if you consider, for example, networking or network attached to persistent memory, right? Then you could also consider the more kind of a radical or ideal approach, which is like single level stores, which means you only have CPU cache and then persistent memory, maybe some DRAM, but not really SSDs. There's a bunch of things that's happening actually recently in the past 2 years with individual database system components. So I'll go over, I think, more on this architectural choices and leave out the individual components offline. If you want to know more, talk to me. So if you think about this, persistent memory, you can take it as a additional tier, right? Then basically the problem here to consider is what's the kind of migration policy between these different layers, right? We're still going to have a buffer pool, but this buffer pool is going to be able to use both tiers here. For example, you can put like semi-cold or warm data in persistent memory, and then really hot data in DRAM, and then maybe super cold data in SSDs. So I'm listing also some papers over here. So these are just the pointers of recent work. Now, the second more radical approach here is like single level PMM engines. And weirdly enough, we don't really see too many proposals kind of out of this direction. That's another rant that I have. When you read papers about PMM, it's all about individual components, but not really much about this, right? But the idea is that you can keep everything in persistent memory. And then this basically is leveraging persistence and byte addressability. So this is where we actually get, for example, instant recovery. But also you will need core data structures where individual components support that's kind of transformed to work with this single level idea. So the key problems and insights here is that basically you have to migrate or mitigate PMM's high latency and lower bandwidth. Remember the numbers we have seen earlier, right? And then, but also this is yet another rant, right? So if you look at all the the papers and the proposals, basically we're trying to compete with main memory, right? And then this basically leads to a lot of approaches. For example, you're going to use main memory to cache or to store part of a data structure in DRAM. And so on, right? And then, but this basically unnecessarily puts systems built for this kind of a vision in a disadvantaged place, right? Because that's not really the goal. What you want to actually to do is to really compare the whole package, meaning performance and also cost, right? So of course, this will be based on the individual components, right? For example, B trees and so on, which we had a tutorial in VLDB, but I'm not going to repeat here. All right, so there's several, actually still some representatives, right? For example, Zen, right? This is perhaps the only one that I've seen so far in terms of getting a whole engine to work in persistent memory. But ironically, if you look at the architecture over here, actually the individual components, or for example, index, is actually volatile, meaning it's using old techniques from main memory database systems to actually support persistent memory systems, right? And really the persistent or instant recovery part is just the actual data or individual tuples. Still, you would have to rebuild your index when the system restarts. Yes.
Conceptually, do you need the DRAM?
Not necessarily. So
level would be.
Yeah, right. A single level would be really CPU cache and then the persistent memory. But typically we still have DRAM because that's another nuance I'll get back to later. Because for a machine you buy today, you have to have DRAM. You cannot boot up the machine without DRAM.
And why? I mean, just you're going to say that.
I don't know why. So some people in Intel would know. So yeah, that's a practical limitation. Okay, so there's a bunch of individual data structures which I listed over here, but I won't really talk about. I think. Okay, so a third one actually even less talked about is actually to build better main memory database systems. And I call this like poor man's Ferrari, because if you think about it, for main memory database systems, again, why it didn't really got super wide adoption might be because the cost is really high, right? Because you have to buy a lot of DRAM. Now, if you have like 1/3 of the price and much bigger capacity, then why can't we use it as just cheaper memory? And then the issue would be, how do you actually try to approach main memory performance? And this is where we actually need to care about main memory level performance, right? But this is not really much attention yet, and we have some ongoing attempts. There are some funny stories I can talk about later, but I'll save it for here. Okay, so individual components, I think I'll just skip this for the sake of time. And let's see how can I do this actually? Okay, I think now we're good. So I'll talk directly about the final part, which I think is the most kind of interesting part. We'll look at the promise and reality. I don't know how many of you heard about bubble memory. Anyone? Okay, all right. So good. Yeah. So this is all over the news, right? And basically, Intel says we're killing this business. And personally, I think this is, I mean, the technology itself is really good, but it's more like a business problem that's happening here. But this is actually not the first time. I'm not going to the bubble memory story yet, right? But even for this, it's not the first time. If you look at a little bit of history, when I started to actually look into this, there were architecture proposals from architecture community back in maybe 2008, 9. And at that time, they're saying, from 5 years now, we're going to have it, right? 2014, apparently it didn't really happen. So then people started to use NVDIM and also emulation because NVDIM already existed at that time. And maybe, then say, well, 3 to 5 years later. So this time it kind of, delivered by Intel and Micron. But then both, fortunate and unfortunate thing is that there's a lot, numerous papers based on just Optane. And then now the only vendor drops off, then what do you do with this, right? So, there's 2 things, right? So why did this happen? And, what should we do now? So I'll try to answer these questions, but I don't know whether it's right or not. So feel free to, tell me if I don't know what I'm talking about. Okay, so if you talk about PMEM, right, kind of data structured and so on, right, there's so many papers already. And now if you say like, so here, basically, if you look at performance, right, faster than flash, cheaper than DRAM, it's really nice. Until you look at the cost. And also in SSD world, you're looking at a lot of these new amazing devices. Things like 3D VNAND or even 3D XPoint itself can be used to build SSDs, right? So some of you might already know this part of the talk from Cider. So bear with me, I'll go to some kind of hopefully new things later. But if you look at the performance of this, for example, P50 100X drive, which is an SSD, but it's using the same material as the Optane PMEM, we're looking at this kind of peak read and write bandwidth, 7 GB. And you can get kind of 400, 800 normal range of capacity. Looking at the same technology, but in a different interface, we're looking at actually read performance, similar, same. Peak write, this is a single DIMM. It's actually quite limited compared to the SSD version, right? So if you look at this actually from the hierarchy perspective, being at a lower level of the hierarchy doesn't mean it's really strictly slower anymore. Now, of course, this is also related to, for example, how many DIMMs you're going to use here, right? So if you use really like more, let's say, 6 or 4 DIMMs even, then you can interleave the writes, then you apparently can get better performance than that, right? But single device perspective, this is actually already happening, right? If you get a machine today, this is what you might actually get, right? So if you consider the cost of an entire server, the kind of story is even more clear, or why this actually didn't work. And when we presented this back in, I think, January Insider, we were saying, this doesn't make economical sense. And we would be happy if you prove us wrong in 5 years, but then, this happened in 6 months. So anyway, so if you try to consider the cost, right? What does it take to actually build a server with PMEM versus SSD? On the left is the PMEM version, right? So there's a lot of population rules and installation requirements. For example, you have to have some DRAM per channel, I believe, to activate the PMEM plug into the same channel, but on a different DIMM slot, right? So that means for the 1/3 of the cost of DRAM, to buy a PMEM, you actually have to buy a DRAM. What's the point, right? And also you have to clock down the DRAM frequency because the PMEM DIMMs actually run on a modified DDR protocol that requires a lower frequency than the DRAM. So that means if you build an SSD server, you can run at full, for example, DDR 3200, let's say, frequency, but with PMEM on the server, then you have to run 2999, right? On the SSD side, it's really flexible. You can do whatever, right? You can have one single DIMM of DRAM, and then you can have whatever number of SSDs. Of course, if you want to do RAID, then you have to follow some population rules, but it's not the same level as this one. And CPU cost is also another thing that I often kind of rant with my students and others. So here, if you think about data movement, right? When you move data, we don't really have a DMA engine, or we don't actually normally use a DMA engine, although it actually exists in the CPU, which is a small, nice feature there, but nobody actually uses it. Is that you're using synchronous load and store instructions to move data. And these are, remember, high-end CPU cores, right? Only Intel has Xeon, Scalable, Gold, or even higher. They're expensive stuff, but use it to just load and store. But on the other hand, for SSDs, right, so you can use asynchronous DMA and then overlap I/O and compute, which is pretty nice, right? Yes.
Arguably, this is an interface argument.
This is more interface, yes.
On paper, CXL fixes
yes, but like I said, there's actually something called IOAT in the CPU that you can actually do asynchronous mem copy. It's just a less known feature.
But in both aspects, the installation, all the over provisioning, the frequency.
Yeah.
On paper, CXL fixes that. On paper.
True, yeah, but well, we don't know how exactly it's going to look like. Yeah.
But they pulled it off the market. So the next generation has CXL in it, but they pulled it off the market before it. So they got released the third generation with CXL, but they've killed the entire business beforehand. So,
yeah. So
we really won't know what.
It's a really weird situation right now. So I actually don't know. Right. So I think I'm doing well on time. Okay. So I'm just showing the final results over here. If you consider per gigabyte price, we're looking at, for example, here $4. I think this is US dollar anyway. Per DIMM, right? So this is really a good number. But if you factor in also the DRAM and CPU, then it suddenly becomes like $18. Yes.
So just to be sure, I mean, I've done some of these calculations myself.
Yeah.
I'm wondering, so you have the 6 times 32 gigabytes DRAM, and I mean, these are more expensive than going 16, and theoretically you could also do 8 gigabytes.
I could, yes.
So
yeah.
I mean, is that like, how low can you go on those costs there? If I
well,
have 6 times 8 gigabytes of DRAM, which for a server would probably pretty small, but then I have like 50 gigabytes of DRAM versus what 1.5 or 4 terabytes of PMEM.
Yeah.
So that, I guess is that much of a cost?
I think the point is to make the comparison with SSD version, right? So then once you do that, it would become a kind of a more significant part, right? Because if you go down, you can definitely have a really small, tiny DRAM. But then in a memory orient or a memory centric system, then that's not really a practical choice. Yeah, right. So basically, cost effectiveness is not there in practice. Per gigabyte for SSD system here, even if you add this DRAM, right? And this is already, I think, kind of put SSD on a disadvantaged place. Even that, we're using just less than $6. And also the CPU cores, they're the same, but I mean, the total CPU cores is the same, but the amount of CPU you use for I/O is really different, right? So here I'm really using the CPU to do load and store, but this one is really just the handling requests. It's, start a request, see pull the request whether it's finished or not, and so on. So I have more details here, but I think we got the idea already. So if you want, I'll quickly go through this. But basically, if you look at the per drive, per gigabyte, cost at the drive level, this DIMM would cost like $4 over here, right? But SSD already it's cheaper over here, 2.666, right? Again, same technology, but different interfaces, right? NVMe versus DIMMs. And if I get 6 DIMMs on the motherboard, then it's bigger capacity, right? But same per gigabyte cost, obviously. But also the kind of a not so nice thing about this is that there's no expansion because I already used all the slots on the motherboard. But for this one, I can still expand, right? And then now you can calculate the total cost with with DRAM, like I mentioned earlier. And then also the CPU cost is quite different. If I consider the amount of CPU cores or hyperthreads I need to actually saturate the drive, this is anywhere between like maybe 4 to like 10 or even a little bit more, depending on the access pattern you have, right? So, but if I use, for example, 10 hyperthreads, this would be the price, like $18, which is the number I showed in the previous slide. Yes.
When you refer to cores necessary to satisfy or to saturate the bus, do you also factor in the need streaming load? And
no, this is like a pure, just a normal 8-byte load and store, like scalar.
If you talk about modern hardware, should we also incorporate?
That's a good point. Yes, yes. So if we consider like the whole CPU, that's even higher number, right? But for this one, if you really look at the numbers, like any CPU cost actually beyond the 1 thread, I can already saturate using 1 thread, the drive, right? So anything beyond the 1 thread is actually overkill. So I actually don't really need that many cores. I just need 1. So that's why you can cut it really down to the bare minimum for the SSD system, right? So it's an overkill. All right, and for this PM6 version, this is the kind of a middle ground where you actually can get a much better performance, cost of performance behavior. So basically, the lesson here is that if you're really shooting for kind of a PMM system, you should really fully populate your machine. But do you really want or need that kind of capacity? That's also another question for the application. All right. Okay, so this basically leads to a lot of more recent development actually going to kind of do the SSD camp, right? So I can use clever data structure designs and also more recent I/O interfaces to actually get near memory performance, even though I'm using a SSD. Right. So we did some simple experiments with persistent memory tailored index structures like B trees and hash tables, and compared them with really class homework assignment grade of code for SSD. So the SSD version is actually performing really poorly. There's a lot of room to optimize, but still the result basically shows that if your workload is really memory resident, just use SSD, don't bother, right? And also for one Optane SSD, same material again, you can actually get comparable performance with one PMM DIMM. So I mean, after all, it's the same material, right? So it actually makes sense. But that might be also another reason why this didn't really pan out again, right? So that's another reason I mentioned. So the performance really doesn't justify the cost, right? So now I'm going to draw some analogy to bubble memory. So like I said, this is not the first time. This is the second part of not the first time, right? Back in the 60s and 80s, until 80s, I guess. So this was the hope. And if you read the papers, like Cousin and Philip already mentioned, if you read, for example, from I think Marco Schelzer in UBC, a lot of the things we say today on today's papers, they're really similar to what we said back in 60s, 70s, 80s about, for example, making things single level and instant recovery, redesign of all the system components and so on, right? But it didn't really make it because of scalability price issues, same issue here, right? And it's complex to make because you have to, for example, change the controller as well. Again, what happened here is the same thing. Then at that time, also DRAM and hard drives, they actually caught up, which is very similar to what's happening today. So we just talk about performance per dollar, right? It doesn't really make economical sense. And SSD is actually getting faster and faster, and it's just much better now. And again, memory controller is more complex. And there's also another killer here, which is a single vendor. Actually, back in the 60s and 80s, it's older than me, but by reading the papers, it looks like at that time we had multiple vendors, and still it didn't really work out. And here, this is an Intel chip, so that's a little bit. It's kind of funny, interesting here. Okay, so I think I have like 7 minutes, so I'll try to talk a little about then now what we should do, right? So are these techniques we proposed still relevant, or how should we actually use them? So one potential we found actually is that they are actually quite effective for also DRAM or main memory environments. Again, so one experiments we did is to use these PMEM tailored indexing structures, but remove all the flushes and finishes because we don't need them in DRAM, and then run them on DRAM. So if you look at the results, this is really just a simple one experiment, right? 8-byte keys and payloads and uniform distribution, and just we have a driver just that keeps issuing the requests and so on. X-axis would be threads, right? This is a normal kind of a scalability curve you would see on a database paper. The FP tree, LB tree, row art here, these are the PMEM tailored indices, and the hot and the mass tree, you probably know that's main memory optimized indices. So these results basically here, I don't require you to kind of differentiate the lines, but that's exactly the point, because you can see very similar performance and sometimes even better performance. For example, this one compared to the DRAM tailored or optimized indices. All right. So, and also another one just recently happened is that we worked on this hash table idea, which is called Dash. And it was proposed for PMEM indexing, right? But then a startup came by and said, "Oh, again, I found this technique interesting, and it's actually quite useful for our DRAM-based, indexing, which they are, developing for replacement or fast replacement for, Redis, right? So this is another use case where these techniques actually, again, it's actually useful for also DRAM environments." Another thing which is about functionality, I didn't really talk too much here, is, well, this is yet another rant when I read papers. So if you again look at the papers or recent proposals, it's more about, let's say, for example, just to make integer keys work. And there's a lot of corner cutting with functionality, like string key support or variable length key support, and handling things like NUMA effect and so on. Right? So those things are actually missing, not only here but also in DRAM-based indexes. So I think that's where we should kind of try to focus on in the future. All right, so I think I'll stop here. So a little bit of summary. I think we talked about what we wanted, better scalability, energy profile, and then these promises of new emerging memory techniques and what actually happened with persistence. So one personal opinion is that maybe we kind of went a little bit the wrong way or side way of looking at persistence too much. But ignored the other aspects, for example, scalability or bigger capacity, and just use it as a bigger memory, right? That might be actually more useful. Well, impact on database systems here, mainly talk about architecture, but there's a lot more in individual components if you're interested. So caveats and challenges, I think, to summarize, I think it's really the cost is too high. That's one. And second is there's only one vendor. So that might make a lot of people hesitant in kind of adopting this technology. But actually, if you look at the landscape of this kind of devices, I think one really promising direction is to look at NVDIMMs, because that's something that people haven't really put too much thought into. But I think really there's a lot of potential. For example, you can actually get instant recovery out of it, right? Although it's a really small device. But for a lot of cases, we don't actually need huge capacity, for example, using it to do logging. And then one other direction, of course, is to work on new technology, right? So SSDs and CXL, like I mentioned. Hopefully, there will be new other talks that will cover this. And then we'll also see how the current work in progress pan out. So I don't think this is really the end of persistent memory system research, but there's certainly kind of a cool down period before the next actual hardware became available.